Hello and welcome. In our previous discussions, we explored how the law of sines helps us solve oblique triangles in several situations, such as when we know a side and two angles, or in the ambiguous case, with two sides and a non-included angle. But what happens when we're given two sides and the angle between them, known as the side-angle side or SAS case? Or what if we only know the lengths of all three sides, the SSS case? In these scenarios, the law of sines isn't enough. We need a new tool. Today, we'll introduce that tool. We will be learning about the law of cosines. By the end of this lesson, you will be able to solve oblique triangles for both the SAS and SSS cases, and you'll also learn a fantastic formula for finding a triangle's area when you only know its side lengths. Let's begin by formally defining the law of cosines. Consider an oblique triangle with angles A, B, and C, and sides of length A, B, and C opposite those angles respectively. Here is a standard oblique triangle. Notice how side A is opposite angle A, side B is opposite angle B, and so on. The law of cosines gives us three related formulas. Each one states that the square of a side is equal to the sum of the squares of the other two sides, minus twice the product of those two sides, and the cosine of their included angle. The first form is a squared equals b squared plus c squared minus 2bc cosine of a. Similarly, b squared equals a squared plus c squared minus 2ac cosine of b. And finally, c squared equals a squared plus b squared minus 2ab cosine of c. Look closely at that last formula. It might seem familiar. It looks very much like the Pythagorean theorem, doesn't it? The only difference is the term at the end, minus 2ab cosine c. Let's explore that connection. What would happen if angle C was a right angle, meaning it measured 90 degrees? If we substitute 90 degrees for C, the formula becomes c squared equals a squared plus b squared minus 2ab times the cosine of 90 degrees. The cosine of 90 degrees is 0. This is a key trigonometric identity. So our expression simplifies, because 2ab times 0 is just 0. And we are left with c squared equals a squared plus b squared, which is exactly the Pythagorean theorem. This shows that the law of cosines is a generalization of the Pythagorean theorem that works for any triangle, not just right-angled ones. Now let's put this into practice. We'll start by solving a triangle where we have a side-angle side or SAS case. For this type of problem, we'll follow a clear, three-step process. First, we use the law of cosines to find the unknown side. Second, we use the law of sines to find the angle opposite the shorter of the two sides we were initially given. This helps us avoid any ambiguity. Finally, we find the third angle, using the fact that a triangle's angles sum to 180 degrees. Let's look at our first example. We have a triangle with sides of 7 feet and 16 feet, and the included angle between them is 95 degrees. Our goal is to find the length of the third side, B, and the measures of the other two angles, A and C. Following our first step, we'll use the law of cosines to find side B. We use the version of the formula that solves for b squared. Substituting our known values, we get b squared equals 16 squared plus 7 squared minus 2 times 16 times 7 times the cosine of 95 degrees. Calculating the squares gives us 256 plus 49, which is 305. The cosine of 95 degrees is approximately negative 0.0872. Multiplying this by negative 224 gives us a positive 19.5. Adding these together, we find that b squared is approximately 324.5. Taking the square root of both sides, we find that the length of side B is approximately 18.0 feet. Now for step 2. We'll use the law of sines to find an angle. We choose to find angle C, because it is opposite the shorter of the two original sides, side C, which is 7 feet. The law of sines tells us that the ratio of a side to the sine of its opposite angle is constant. So C over sine C equals B over sine B. Plugging in our values, we have 7 over sine C is approximately 18.0 over the sine of 95 degrees. Rearranging to solve for sine C, we multiply 7 by the sine of 95 degrees and divide by 18.0. This gives us approximately 0.3873. Taking the inverse sine or arcsine, we find that angle C is approximately 67.2 degrees. Finally, for step 3, we find the last angle, A. The sum of angles in a triangle is 180 degrees. So angle A plus 95 degrees plus 67.2 degrees equals 180. This means angle A is 180 minus 162.2, which is 17.8 degrees. We have now completely solved the triangle. Next, let's examine the side-side-side, or SSS, case. This is where we know the lengths of all three sides but none of the angles. The strategy here is slightly different. First, we use the law of cosines to find the angle opposite the longest side. This is important because this angle could be obtuse, and the cosine function handles this perfectly. Second, we use the law of sines to find one of the remaining, necessarily acute, angles. Third, we find the final angle by subtracting the other two from 180 degrees. Let's work through an example. We have a triangle with sides of 23, 29, and 41 centimeters. Our task is to find all three angles, A, B, and C. According to our plan, we start by finding the angle opposite the longest side. The longest side is C, which is 41 centimeters, so we'll find angle C first. We'll use the law of cosines formula that involves angle C. Plugging in the side lengths, we get 41 squared equals 23 squared plus 29 squared minus 2 times 23 times 29 times cosine C. Calculating the squares, we have 1681 equals 529 plus 841, which is 1370 minus 1334 times cosine C. Now we need to isolate the cosine C term. It's a common mistake to subtract 1334 from 1370 here. But remember that 1334 is multiplying cosine C, so we must first subtract 1370 from both sides. This gives us 311 equals negative 1334 cosine C. Dividing both sides by negative 1334, we find that cosine C is approximately negative 0.2331. Since the cosine is negative, we know the angle is obtuse. Taking the inverse cosine, we find that angle C is approximately 103.5 degrees. Now for step 2, we use the law of sines to find another angle. Let's find angle A. Setting up the ratio, we have 23 over sine A is approximately equal to 41 over the sine of 103.5 degrees. Solving for sine A, we get approximately 0.546. The inverse sine of this value gives us angle A as approximately 33.1 degrees. Finally, we find the third angle, B. Angle B is simply 180 degrees minus the two angles we've found. That's 180 minus 136.6, which gives us 43.4 degrees for angle B. And with that, the SSS triangle is solved. The law of cosines is not just for abstract triangles. It's incredibly useful for solving real-world problems. Let's consider a practical application. Imagine two cars leaving a city simultaneously. Their highways diverge at an 80-degree angle. One travels at 60 miles per hour, the other at 50. We want to know the straight line distance between them after 90 minutes. First, let's model this situation. The city and the two cars form the vertices of a triangle. The distance between the cars will be one side of this triangle. Next, we need to find the lengths of the other two sides, which are the distances each car has traveled. We use the formula distance equals rate times time. An important first step is to convert our time into hours to match the units of the speed. 90 minutes is equal to 1.5 hours. For the first car, the distance is 60 times 1.5, which is 90 miles. For the second car, the distance is 50 times 1.5, which is 75 miles. Now let's visualize the problem. We have a triangle where two sides are 90 miles and 75 miles, and the angle between them at the city is 80 degrees. This is a classic side-angle side, or SAS case. We need to find the length of the side C opposite the 80-degree angle. We can apply the law of cosines directly. Using our formula, c squared equals 90 squared plus 75 squared minus 2 times 90 times 75 times the cosine of 80 degrees. This simplifies to 8,100 plus 5,625, which is 13,725, minus 13,500 times the cosine of 80 degrees. This gives us approximately 13,725, minus 2344.25, resulting in c squared being about 11,380.75. Taking the square root, we find that c is approximately 106.7 miles. So after 90 minutes, the two cars are about 106.7 miles apart. We've mastered finding sides and angles. But what if we need to find the area of a triangle, and all we know are the lengths of the three sides? You could use the law of cosines to find an angle, and then use the area formula 1/2 AB sine c, but there's a more direct method. This method is called Heron's formula, named after the ancient Greek mathematician. Heron's formula provides a beautiful way to calculate the area, using only the side lengths. The formula is, the area is the square root of s times s minus a times s minus b times s minus c. Here, a, b and c are the lengths of the sides, and sine serix is a special value. As is the semi-perimeter of the triangle, which is simply half of its perimeter. You find it by adding the three side lengths together and dividing by 2. Let's apply Heron's formula to an example to see how straightforward it is. We need to find the area of a triangle with sides measuring 7, 11 and 9 feet. The first step is always to calculate the semi-perimeter, S. We add the side lengths, 7 plus 11 plus 9 equals 27. Then we divide by 2 to get the semi-perimeter, which is 13.5. Now that we have S, we can plug everything into Heron's formula. We substitute 13.5 for S, and 7, 11 and 9 for A, B and C. This gives us the square root of 13.5 times the quantity, 13.5 minus 7, times 13.5 minus 11, times 13.5 minus 9. Let's calculate the values inside the parentheses. This simplifies to the square root of 13.5 times 6.5, times 2.5, times 4.5. Multiplying these four numbers together gives us 987.1875. Finally, we take the square root of that number, which is approximately 31.4. Since the side lengths were in feet, the area is in square feet. The area of the triangle is approximately 31.4 square feet. Let's quickly recap what we've learned today. We've added two very powerful tools to our ability to work with triangles. First, we mastered the law of cosines. It's our go-to method for solving oblique triangles, when we are given either two sides and the included angle, SAS, or all three sides, SSS. It's a generalization of the Pythagorean theorem for all triangles. Second, we learned Heron's formula. This elegant formula allows us to find the area of any triangle when we know the lengths of all three sides, without needing to know any angles at all. These methods are fundamental in fields like engineering, physics, and surveying. Understanding them well will be a great asset. Thank you for your attention.